Okay, so we now come to this scenario of measurement uncertainty. That's the other kind that we have to explore. And loosely speaking, it would be statements like P and Q, like the momentum measurement and a position measurement, cannot be measured jointly on the same device, that is, measured jointly. And that always means cannot be done without error. Right? So you can make some sort of joint measurement, we'll talk about that, but you'll incur errors if you do that. And another kind of statement is these measurements disturb each other. And that is actually what people have taken from Heisenberg's paper. So that is, so this idea of disturbance. And that is definitely not in the preparation uncertainty relation that we looked at before. So let us look at an abstract version of Heisenberg's microscope. Right? So we are preparing some particles. And then the first thing that happens is a measurement of position. And by using the microscope, that is, you look at the particles with a microscope. And you get some reading on the microscope, some picture on your screen, and what you see there is an approximate version of position. So I put the twiddle here on the Q, indicating that this is not exactly a position measurement, but it's an approximate version of it. And then we look what happened to the particle afterwards. So that would be like a P measurement. Now, in these pictures, so first of all, it's important to note that there is a value x, let's say, coming out, a measured value, and also the particle goes on, and we can think about what happens to the particle afterwards. So in these pictures, the letters P and Q stand for everybody's position and momentum observable as you find them in the textbooks. Just as they're defined there, they give you these probability distributions that you learn how to compute. And the twiddles means you something slightly else, right? So this is an approximate measurement. Definitely, in the microscope, you don't just see the position. That is Heisenberg's point, because you have to really analyze how the particle interacts with the light of the illumination in the microscope, and that will change the momentum, for example. Right? So, okay, so this is an approximate version. Now, how do we talk about the errors here? And so actually in Kennard's early paper, he already explains that quantum mechanics has a special relation to this. Right? So in classical physics, you can say there is a true value, and our aim of a measurement is to uncover the true value. And then the error would be the deviation between what you measure and what you should have gotten. Now, this notion of the true value doesn't exist in quantum mechanics. That's what Kennard actually already points out. There is no true value, and so you cannot simply talk about this kind of deviation. But what we can always do is make both measurements and compare, right? And that's what we are going to do, so we can make the same measurement, and then in this box I just write a Q, which means the standard everybody's position measurement. So that gives you another value. Let's call this, maybe x twiddle would be a good notation here, and call that x. And now we have to do some kind of comparison. And then let me just write a delta here for making the comparison. And we have to discuss how we do that. But really we have two experiments. They're both statistical experiments, and they both produce distributions, probability distributions for that microscope measurement and probability distributions for the position. In general, these distributions will be different even if we take the same state, right? So this delta will be a comparison of distributions, of probability distribution. And there's a quantitative way of doing that, which I'm not going to discuss in detail right now. The basis of the comparison is running these two statistics experiments and then comparing the distributions. Okay, and then this will give us some version of a deviation of these two measurements, and that will be a figure of merit for the accuracy of this QTwiddle as a position measurement. Now, the other thing that we can do, that is also in this theme of disturbance, we could take our particles. We don't care about the microscope, we just measure the momentum. And of course, these are different experiments, and so here we get some p's and some, call them p prime or so. And we can do the same thing. We compare what comes out of these, and again, we have to make some kind of comparison. Now, every particle either runs in this experiment or in that experiment. So it's not a question of the individual case. But again, we can compare the distribution. So what we are doing in the end is, so this microscope situation gets analyzed by making both of these comparisons. That will give us something like delta Q. This will give us something like delta P. And the claim is that you cannot make them both small, right? So if you make them, draw them in an uncertainty diagram, as we did with the declaration uncertainty, then there's white space at the bottom, right? You cannot get both small. Okay, so this is the basic scenario of disturbance by measurement, but also a relation with the accuracy of this approximate intermediate measurement. So this is precisely Heisenberg's scenario. But let us build onto that a little bit, right? So sometimes you read that the measurement introduces an uncontrollable disturbance, right? So this disturbance that is somehow, so this state is different from that state, right? Something changed under the microscope, physically we would say by the interaction with the illuminating light. So this change, after all, we know exactly how this thing works. So we might actually try to undo this. And that is my second version of this. So let us do something slightly different, right? So we make this approximate measurement. We take good old microscope. But then we don't just measure the momentum afterwards, but we try to make a measurement that reconstructs as well as possible the momentum before, without the microscope, right? So what we do here is, so this thing here is a reconstruction measurement. And let me describe it for you. So this is a device that is purpose built to perform well in this kind of comparison. So that is, we are allowed to use the outcome of this microscope measurement, and of course we are measuring on the state after the measurement. So these are the inputs to this reconstruction, and we will build this not just as a momentum measurement, but with the aim of optimizing this comparison. And in that process, of course, optimizing means that we use everything we know about this thing and undo computationally what we can, right? So if we know the outcome and see the state, then in classical physics, you could pretty much reconstruct what the disturbance was. And then you can just compute what the value before should have been, and that is the sort of output that we get here. So it's like a maximally reconstructed thing. But the basic story actually remains the same, right? We have a comparison of, this is the accuracy part, and the disturbance part now is the best you can do in the way of disturbance. That is the best you can do in the way of reconstructing what the direct momentum measurement would have given, right? Okay, so let's go one step further in this abstraction, right? So what we do now is we still stay with the same philosophy, how to compare here. But what we really do is we just take this whole stuff as a single device. Because it doesn't really matter what we do inside here. For example, we could measure the momentum first and then the position, or have some other strategy. The only thing that we're looking at now is that this thing produces an X twiddle measurement and some kind of a P twiddle. An X twiddle outcome and a P twiddle outcome, right? Okay, so let's do it like that. And this, everything that I said before still applies. So this is now what we would call a joint measurement, or if you wish, an attempt at joint measurement. The only thing we need to know about this is that it's a kind of measurement that produces an X value and a P value in every single run. And so then we can look at these distributions and compare. So these distributions that are actually being compared here are called the marginal distributions, because I make this comparison just on the basis of the X twiddle values, and I don't look at these guys, right? And this comparison, I just look at the P twiddle values and don't look at these guys, right? But the whole thing now is completely symmetrical in P and Q, right? So P and Q play exactly the same role. So we are generalizing Heisenberg's microscope also to a situation where you maybe first measure P and then measure Q in some way, but also allowing any strategy for producing these two values. And so actually in these two themes that I noted above here, the disturbance part, I actually consider as a special case of joint measurement. Right? So actually, if we get bounds for joint measurement, we automatically have made bounds for the quality of the disturbance. And now, so I still owe you an explanation how these deltas are actually made, but believe me for the moment that you can. And there is a definition for these deltas, so that actually the inequality now becomes delta P times delta Q. Those are the ones that I get from these comparisons. For any attempted joint measurement is larger than h bar over 2. So that's the result of a theorem now. It's only a theorem if I tell you exactly what the deltas are, but that has been done, and I proved that in 2007. So it's a bit tricky here. Of course, it looks exactly like the preparation uncertainty relation, but the deltas mean something totally different, right? So they refer to this scenario of a joint measurement, and they have nothing to do with variances of these particular measurements or so. And it's a bit surprising that actually the same comes out. So you could say that Heisenberg himself never made this distinction between preparation and measurement uncertainty. For him, it was about knowledge, and he didn't care how you acquire the knowledge, right? But I think it's a very useful distinction. Well, what he calls a proof doesn't really work, right? So it's bad mistakes, but still the idea is correct, right? So we can prove this in that sense. But does it always have to be the same? So maybe we missed something, some connection between the measurement and the preparation side that says that no matter what the observables are, because of course this can be written down for any pair of observables. So you can replace P and Q by I don't know what, right? Angular momentum measurements, whatever your favorite is. And then you can discuss the same question, and you're looking for bounds that are independent of the way you're trying to do that. Okay, so do they always have to look the same as the preparation uncertainty? Well, the answer is no. And we did this in great detail. And there's one class of cases where it works, and that covers, among others, this position momentum, but also every situation where P and Q, these observables, are technically related by a Fourier transform. So being related by a Fourier transform is actually what you need here. And this Fourier transform can be a generalized one, so that the P would be sigma x, a sigma x measurement. This would be a sigma z measurement, and the Fourier transform is a Hadamard transform. Right? So in quantum information, we immediately have cases of this, where also this equality holds. And I will discuss that in later videos. Okay, this would be it. just describing how do you formalize, how do you go about describing measurement uncertainty.